Hello and welcome to our presentation on the chloroalkali processes in industry. These can be split down into three: the mercury process, the diaphragm process, and the membrane process.
Hello, this is the mercury process, which is the first of the chloroalkali processes which we'll be presenting today. The second process will be the diaphragm process, and then the membrane process. The mercury process was the first one that's developed, and it is in fact a two-part process. This diagram represents the first half of the process. Broadly, the cell is constructed so that the anode is here. The cathode is actually formed by a pool of mercury at the bottom of the cell, which is in direct contact with the base of the cell. The size of the cell is usually insulated with rubber. So sodium chloride will come into the cell. There's our sodium chloride coming in. And being in solution, we have this positive sodium ion and the negative chloride ion. Now, the chloride ion will be attracted to the anode, where the anode donates an electron to the chloride, and this forms then chlorine gas, which passes out through the top of the cell. The sodium is attracted to the cathode, where it forms an amalgam with the mercury. And now, an amalgam is essentially an alloy containing mercury. And mercury forms alloys with many different types of metal. In fact, the only metal it doesn't form an alloy with is iron. The sodium then passes along with the mercury, which is pumped around the process, into the second cell. So this is the second part of the process. This is the second part. This is not actually an electrolysis cell. It's merely a place where the sodium hydroxide is formed. The construction of the cell, basically this part here we have water, and here we have our amalgam of mercury and sodium, and at the contact between the mercury and the water we have a bed of beads of graphite which acts as a catalyst for this process. Now the sodium comes in from the first part of the process, being carried by the mercury, and it enters solution, forming our sodium hydroxide. Now the concentration of sodium hydroxide that can be reached here is approximately 50%, which is a lot for sodium hydroxide, and once a suitable concentration has been reached, the sodium hydroxide exits. The mercury cycles round back to the first half of the process, and more water enters so that more sodium hydroxide can enter solution and be carried off. Okay, so the advantages of the mercury cell process. This process has the best rate of all three of the processes and the smallest footprint. Also the least energy requirement per tonnage. So energetically and space-wise this is a very efficient process. The sodium chloride that the process uses as a foodstuff doesn't actually have to be of great quality, and the process produces sodium hydroxide at about 50%, which means you don't actually have to concentrate the sodium hydroxide further to get the solid out, which is a great advantage in terms of energy. The problems with the process, now the sodium hydroxide produced tends to be of quite poor quality if the feedstock is also poor. There's no purification in the process, and the sodium hydroxide can also contain small amounts of mercury, which brings us on to the second point, which is this process uses large amounts of mercury, which is environmentally can be a very damaging compound, and historically there have been incidences of widespread and very severe mercury poisoning from industrial processes, so its use is discouraged. And that's the mercury process.
Okay, so you've just seen Nigel and the mercury process, and now we're moving on to the diaphragm process. Now this is a little different, so I've just got this diagram to help us break it all down. So we've got the anode and the cathode, which is usually separated by a diaphragm of asbestos, hence the name. So you've got the saturated brine that enters here in the form of H2O and NaCl. The chloride ions from the NaCl are then oxidized in the anode chamber, where they are allowed to escape through here, and are then stored. But then what you'd see to the water happen on the cathode side is you'd see the water getting broken down into hydrogen gas and dilute caustic soda. So this dilute caustic soda leaving the chamber here will have to be concentrated to around 50%, and the salt needs to be removed through a process of evaporation that uses 3 times the tonnage of steam that it takes for one ton of soda, which is crazy. Well, then what we get is this salt that can be used to saturate the dilute brine, which is very useful. And then what we'd have to do with the chlorine gas is purify it using a method of liquefaction and evaporation. And once we've done all these factors, that's the whole process, going through one cycle. And that's the diaphragm cell method.
Right, so this is the chloroalkali process using the membrane cell method. In this method, we've got the electrolysis of sodium chloride or brine. So sodium chloride, aqueous sodium chloride comes through here, and the chloride ions are oxidized to chlorine gas by the anode. And the anode, it is important for the anode to be titanium because chloride ions are very corrosive. And the equation for this would be two chloride ions which form chlorine gas and 2 electrons. And the chlorine gas that is produced comes up through here and is collected and stored here. Now in the second chamber of the membrane cell, we've got water that comes in through here, and the water is reduced to hydrogen gas and hydroxide ions. So the hydrogen gas comes up through here and is collected here, and the equation for this would be 2 H2O plus 2 electrons, which means water has been reduced to form 2H2 and OH ions. So the most important thing about this method is the non-permeable membrane in the middle. Now this membrane stops the chloride ions from passing through and the hydroxide ions from passing through. It only allows positive ions such as sodium that can pass through and react with the hydroxide ions here and form sodium hydroxide. This can be shown by the third equation here. So if we got sodium chloride plus 2H2O, we've got chlorine gas, hydrogen gas, and NaOH, sodium hydroxide or caustic soda, which is the purpose of this method of producing caustic soda. Now it is important that this membrane stops these two reacting, because if these were not separated, we would get the formation of chloride or hypochlorite. So sodium chloride or hypochlorite. So if the temperature is under 60 degrees, we would get chlorine reacting with coming through and reacting with the hydroxide ions, and this would form chloride ions, sodium chloride and chlorate and water. If the temperature, however, was over 60 degrees, we would get chlorine reacting with the hydroxide ions to produce chloride ions and sodium hypochlorite and water. So it is important to have a non-permeable membrane here, because if we didn't, the chlorine and the hydroxide ions would mix together and form chlorate ions or hypochlorite ions. And this depends on the temperature. If the temperature is under 60 degrees, we would get chlorite ions being formed. So chlorine gas reacts with the hydroxide ions to form chloride ions, chlorate ions, and water. Whereas if the temperature was above 60 degrees centigrade, we would get the chlorine reacting with hydroxide ions to form chloride ions, hypochlorite and ions, and water. And that's the membrane cell method.